You think it's going to be bad? Oh my gosh. Is there a curve? Yeah, curve, that's great, right? You know, we have to grade first before you can talk about the curve. Yeah, you know, so anyway, so you have another final exam coming. The study for the final exam begins today, right? When is your final exam? Do you know?
December 14th.
14th, yeah, so it's not that, you know, after Thanksgiving. You know, a few more weeks left, right? Okay, so I haven't seen the exams yet. But what they're going to do is to scan the exams in your grade scope, and then we'll go through the grading process, and you will get the grades hopefully within a week on grade scope, just like you got last time. And then you'll be able to, you know, ask questions about the grades and make changes and so on. So unlike AutoLab, you know, there's a lot of things. If something was not graded correctly or not given partial credit, you will be able to get that, right? Okay. Yeah, okay, so so today is going to be on efficiency analysis. You know, why do we talk about this? Mostly because, you know, you know how to write programs now, right? Kind of, you know, then you also you spend a lot of time debugging things, because I think you spend a lot of time debugging. Right, debugging is about getting the program right. You have to get the program right first before you can think of anything. But that's not the end of the story, okay, because the programs you've been doing are really programs that are really small. They're not big, right? So, but real world programs, when you become a real a professional programmer, you have to deal with a lot of data. Okay, so that's why we talk about these, the efficiency analysis. In other words, okay, your program is correct, it's running, but is it efficient? Okay, what do we mean by efficient? That means, is it going to run in a reasonable time? Right? It needs to run in a reasonable time before you can really do things. I've run programs in my life, you know, all the projects I've been doing. Sometimes I have to let the program run overnight because there's so much data to process, and it'll take overnight to run. That's okay as long as you're waiting for something good to happen in the morning, right? But, you know, by the time you come back, if the computer has crashed or something else has happened, that's not good news. But anyway, the goal here is to understand the efficiency. So today's lecture is going to be somewhat mathematical. In other words, you know, the computers, when people talk about computers, in the early 50s, long before the computer was built, there was this mathematical model of computers called Turing machine. You may have heard about that. That was invented by Alan Turing, who was just across the, on the other side of the town at Princeton. He was at Princeton, he got a PhD from there, I think, in mathematics. And the Alan Turing, there was a movie too, right? Did you guys see the movie?
Mm-hmm. Yeah.
Turing, what does that called? What? Imitation Game, right? It was
Okay, well.
Yeah, it's a good movie, right? So Alan Turing is responsible for all your miseries today.
Jeffrey.
In some ways, you know, he kind of explained, you know, he studied computing long before the computers were there. In other words, he asked the question, what is computable? In other words, what problems can be solved by a machine, mechanical or digital machine? And then if you can solve it, how do we solve it? We call that the algorithm, right? And then the third question is, if you can solve it, will it terminate at a reasonable time? Right? Will the program run in a reasonable time and terminate? Okay? And then he also asked the question, can all programs be computable? Are all programs computable? The answer is no. Okay, so there are a lot of things that are not computable. In other words, you cannot write a program to check whether someone else has an infinite loop. Okay, you cannot write a program to check whether someone else or program has an infinite loop. You cannot do that, right? Because how would you know? And in fact, you know, we don't have to do it using a computer. You can mathematically prove that's not possible. Okay, so there are things that are not undecidable. They call it undecidable. Because in computers, you think about everything as like a deciding problem, right? It's a decision problem. Can you sort this? Can you search this? Can you find the duplicates? So the answer is either yes or no. Right? For the most time, answer is yes, we come up with a way to do it. Right? So the efficiency analysis is going to deal with that. So we talked about the sort of the basic ideas of the runtime of a program depends on many things. The number of processors. When I was your age, I think we only had one processor, so it was just a single processor machine. Now you guys have like 8 processors, right? Maybe 4 processors, at least 4, I think. Right? These are like, so essentially you have like a parallel machine that runs, you know, in parallel. You know, it's like you have 4 computers inside one laptop, right? You know, they are doing independent things. So it depends on the number of processors, the operating system, whether we have Windows or operating OS 1 or whether OS 10, I guess, right? And Linux or something like that. And then it depends on the language of the compiler. Like we said, Java is a slow language. C is a faster language. So if you decide to write some program, you have to choose the proper language for the program. For example, if you have a number crunching program, or if you have a lot of numbers to crunch, I wouldn't choose Java. I would choose something like C. Right? If a program needs safety, maybe Java is a good one, but as long as you don't process a lot of data. If you hear the recent Boeing plane going down in I think it's in Indonesia, right? 160 people died. You know what the problem was? Software. Right? So it's very sad to hear those things because someone like you, I'm not claiming you're going to write a program like that, but someone wrote code that really took away the control of the pilot, and when it was going in a nosedive, it was just going in a nosedive. It was doing the wrong thing with the wrong data set. So that means the program is incorrect. Right? So programs, you know, we don't think about software as life and death, but they are. You can see that if you make a mistake, because everything runs using software now, so if you make a mistake, you know, it can cost lives, which is the biggest loss you can have, right? So it's really a important thing to write good software and make sure they are good, they run fast, they're safe. And computer architecture, there's a course called computer architecture. If you continue in the computer science, you will probably take this course. Network speed is, of course, important because you could have, you know, you're running a program over a slow network, your internet connection is not that great, you know, your program runs slow. So so these are all things that we cannot really control. This means they are very custom to the situation. So the only thing we can control is we measure the efficiency of an algorithm based on a few things. How many total operations does the algorithm take to complete the task? And then we ask the question, how much memory is used by the algorithm? So let's try to sort of take a simple example to see how that works. Okay, so this is a very important topic if you really want to be a computer scientist, because the computer science is not about programming, right? So you guys, if anyone thought that the computer science is about game programming, you're in the wrong place, right? You should just go take a game programming course and you can get a job and program. But computer science is much more than that. It's all about analysis and mathematics and so on. So let's take a program like this. So let's say that we say temp is x, x is assigned y, and y is assigned 10. So we ask the question, how many operations, we did this in the beginning with the pseudocode, now we can do it with the real Java code. How many operations does it take, right? So when you think about operations, there are a few kinds of operations. So we say operations are, okay, wait, let's call them assignment operations. Assignment, comparison, increment, so assignment means you assign one variable to another. Comparison means you compare two variables. Increment means you increase something by 1 or 2 or something like that, right? So how many operations you're doing here? These are, all three are what? Assignment operations, right? So we are doing like, in this case, we are doing like 3 operations. Okay, 3 operations. But what if I wrap this in a loop? So let's say that I have for int I equals 0, I less than n, I plus plus, and then I put this piece of code inside the loop. Now how many operations it takes?
3
So,
times n.
yeah, 3 times, okay, 3 times n, yeah. So once I do the thing, then I will get 3 times n operations. Because each of those 3 operations are done n times. Okay, 3 n operations. So I'm going to introduce a little notation. I think you saw that the other day too. The Tn is the, let's call it number of operations. Okay, number of operations to process n data. Okay, n units. Let's call it units or data size or whatever. Data size. Okay, so in this case we can say Tn is equal to 3n. Okay, 3n is equal to Tn. Tn is equal to 3n. All right. So what we are saying is that the number of operations for this particular algorithm is 3 times n. Okay, but you can imagine that the operations, number of operations, kind of can be compared to the time it takes to do this, right? Because each operation probably takes about a microsecond, because your computer can run like millions and millions of operations per second, right? So even if you think that your computer can run million operations per second, that means each operation only takes microsecond. So I can't even measure this using my timing thing I did the other day, right? I can only measure by milliseconds. So millisecond is thousand of a second. So they're really fast to do that. And then we ask the question, how much memory is used by the algorithm? Okay. So in this case, you can say, in terms of the memory, we don't, I think if you assume that temp is an int, x is an int, y is an int, and then I is an int, right? So there are 4 variables, so the amount of memory used by that program, okay, amount of memory used by that program, you can say it's like 4 times 4. 4 is like int is like 4 bytes. Okay, so you can say that it uses 16 bytes of memory because you have I and temp and x and y all are going to contribute to the memory, right? Okay, then we can ask the question, is there a way to look at the best case, average case, all that will come to that. I think in this case you will realize that there is no real best case or average case or worst case here, right? Because it's going to do its thing, right? You know, unless you have like a conditional, if this, you know, break out of it. So there could be a best case there because you might stop it sooner, right? So you have to figure out when you're going to stop. Okay, take a look at this. This is the program we wrote a while ago called reverse, right? What it does is to take an array of integers, reverse it, and then return an array of integers. So the way it does is, okay, let's take n to be the length of the array, and it goes from 0 to length over 2. Okay, and then it swaps the a's of I and a's of n minus I minus 1. What that means is really when I equals 0, it's swapping a's of 0 and a's of n minus 1. Right, so it's first and the last, the second and the next to last, and so on. So you keep swapping a half the length. By the time you're done with this, you have actually reversed the array. Okay? All right, so what we're trying to do is to understand how much is memory is used by this program. Okay, so we have to think about, so let's say that, I said there's going to be a lot of mathematics, so I'm going to be writing function-like notation. Let mn be the the amount of memory used for n data set. What I mean by n data set is just a data set with n things, right? Okay, so who wants to give it a try? All right, so let me ask questions here, right? So keep you guys a bit more active, engaging. How much memory is used here?
4.
4 bytes, okay? And how much is memory is used by the array?
8 times 4.
Yeah, 4, n times 4, yeah. So the array, so let's say the array A uses 4 n bytes. Yeah, this is the array A. Uses 4 n bytes. And then this n is 4 bytes. There's an I here, that's going to be 4 bytes. Okay, and then what else? Temp, it's going to be another 4 bytes. Right, so what else? So how much you have to add here? It's going to be 4 plus 4, that's going to be 8 plus 4, that's going to be 12, right? Okay, so the memory function, so the other variables use, did I say 12? Yeah, 12, right? So 12 bytes. So we write a formula like this. M of n equals 4n plus 12. So memory used by n things is going to be some function of n. Okay? All right. Can we estimate the runtime? I mean, can we do like I did a memory analysis, right? Can we do like T of n for this program? What's T of n for this one? T of n is how many operations, right? That's what we mean by T of n. Okay. You like mathematics, right? Yeah. Of course you like math.
No.
Right? Yeah. Okay. Yeah, you should like math. Right? Math is good because it explains the world. Yes, it is good. Just like, your calculus, of course, may be horrible, but math is good overall, right? Yeah. Any questions? I want to ask you that. So think about how many operations it's doing here. What is this one here? What type of an operation is that? That's an assignment, right? It's an assignment. Hmm? Yeah, you said assignment, right? Okay, so you're right. You use Savini, right? Savini, your name? Savan. Okay, Savan. Savan is right. Okay, so here, here's another assignment, right? What is that? So that's another assignment here. And then you have 3 assignments inside. So essentially, this is exactly the same code we were looking at before, right? So you have 3 operations here. You do it how many times? How long this is running here? So 3 operations here, right? How many times it's running? It's n times, right? So again, I'm going to ignore the what's inside the loop. Inside the loop also something happening. Okay, like you're initializing, you're comparing, you're incrementing, and all that. But I'm going to ignore that. Okay, I'm just going to look at this assignment, this assignment, this assignment. So these 3 assignments run how many times? N over 2 times, right? Okay, so we will write something like this. We have 3 assignments that gets implemented n over 2 times. Why did I say n over? Because it's running only half the time, right? N over 2 times here. Okay, plus 1 assignment here. So I'm just going to add 1 to it. Okay, so here's the Tn for that. So again, all I'm doing is just looking at assignments. I completely ignore the loop. So again, you will realize soon that it's okay to ignore these things because For the most part, the whole thing is going to depend on n. Okay, so best, average, and worst cases actually depends on n. For example, here, it doesn't really, so what is the best case, worst case, and in other words, is the best case better than the worst case? Is the best case better than the average case? Here, it doesn't matter, right? No matter what data you have, you're just going to do all of it. Yeah, so in this particular code, the best case, average case, worst case, all the same. Exactly the same. All right? Okay, so here's another one here. But this might have a best, average, and worst case that can be looked at. So here, this one says search an array for this target, right, and return a boolean. So it goes through the entire array from 0 to length minus 1. If SY equals target, return true. If you go all the way here, return false, right? Now, I know you guys had a break statement in the exam, right? So if you have a break here, so for example, if I say return, if I say break, because you only break with a condition, right? You don't just break. Because if you just break, then you just break, the first one, right? You have to have a condition to break. You can say if something is true, break, right? So if I replace this by break, right? It will do the same thing except it doesn't return anything, right? What it will do is it will go out of the loop and it will go here. So if I replace this by a break, it will return false, always, right? No matter what, because it will never return true. Okay, so let's count for this search program, let's count the operations, okay, first. I think it's important to know the memory, the operations more than the memory. So for the search, what is Tn? So I want to write again, Tn is the number of operations or time to run n things. You can think like that. Okay, so anyone want to think about this? What type of, ignore the loop again, okay, because if you go into the loop, there's a lot to worry about. What do you do? What kind of operation is that?
Comparison.
That's a comparison, okay? So you only do one comparison here inside the loop. And you do it n times, right? So you do n times. So therefore, what you can do is you can say, okay, this is going to be 1 times n, because one comparison n times, okay? That's about it, right? There's nothing here. Other ones are like return and other things. So that's it. So this function is then, for the search function, is Tn is n. All right, so this is what we're learning. We're learning to count the what's happening inside the loop and then figure out a function. Okay, so the big O is the big word that you're going to hear today, right? Is the notation for describing efficiencies of a program. So in other words, we're going to come up with some kind of a mathematical language to talk about the best program. In fact, when I was at the other institute, for instance, we had for every programming assignment we had a competition, right? Which is sort of like students write programs, and then they will submit their programs so that it will time how long it takes to run them. So we had like a leaderboard where people are competing for the best time. Right, so everyone had like a screen name, so no one knew who the other person was. And I also had a screen name, so people didn't know I was to submit my solution. And students think that it's another student, they try to beat you. Sometimes I get beaten, I have to admit that, because they will be very smart in fixing things. So how do you make your program run faster? You remove some loops, you remove some unnecessary assignments, because if you do the same thing again and again, it's unnecessary. It's going to slow down your program. So you can optimize your program by tweaking it. Yeah, right now, you're not worrying about that, but but as you go in the next course, in particular, you have to make sure your program's going to run. Okay? Otherwise, it's going to be a problem. So here are some functions that you haven't seen all of them in one. So it's sort of like this is like a constant function. Constant means that it's always a constant, okay? Doesn't change. Oops. And this one is called the logarithmic function. Okay, this is like the linear function. This is like fn equals n. This is like the quadratic function, like fn equals n squared or something here, right? And these are like exponential functions, like 2 to the n, things like that. So you can see that, you know, if the number of, as the number of elements go up, go higher, the operations go higher for these kind of programs. So you can see that here, the difference between a quadratic thing, so if you come up with an n squared thing, and an n thing, a linear thing, is getting wider and wider and wider as you go. Yeah, as you go, get n more and more, it gets slower and slower and slower. Okay? So if you have to do more operations, it's more and more slow, right? Okay, so here's a workshop for you guys. Let's do this. I know you can do this, right? Order the following functions from slowest to the fastest. Okay, when we say fastest, it's the smallest function. So the question is, what is the fastest program, which is the smallest function, right? So out of these functions, you know, you can think of this as En if you want to. Log n 1, n plus 2, n log n, 2n squared, n cubed. What is this? That's the square root of n, right? The square root of n. Okay, so which one goes first? What is the smallest guy? 1 is the smallest guy, right? Okay, so we write 1 as the smallest. What's the next smallest here? What's that?
Log of n.
It's not n, right? Log n, okay. Log n, right? What's the next one? What about square root of n? Where does that go? Is it bigger than log n or smaller than log n? Square root of log n.
Bigger.
I mean, square root of n.
Bigger.
Okay, let's, yeah, there could be a discussion here, but let's say that square root of n is bigger than log n. Okay? What's the next one? We're not, I'm going to put a question mark here because I haven't really proved to you that it's actually true. Right? I have to be able to prove or do something with it. Okay, what is the next one? It's n, right? Oh, then n plus 2, right? And these two guys are really close. I mean, they're not much difference if n is very large, right? If n is like 1,000,000, who cares whether you add 2 or not? They're almost the same function. Okay, what's the next one? So the next one is called n log n, right? N log n is the next in the order. What's the next one? Uh, 2n squared. Right, 2n squared is the next function. Okay, so again, what we're trying to do is to think about a different efficiencies in programs, because you may write programs that can fit into any one of these things. Okay? We have already seen programs like running with n times, like Tn equals 3n. Right? That would be like a, you know, I would put in there, right? Put the program there. What's the next one?
N cubed.
N cubed. Right? I didn't put 2 to the n. Where's 2 to the n? I didn't put 2 to the n, but 2 to the n, you would agree, would be bigger than n cubed, right?
Yeah.
Where's n factorial?
Bigger.
It's even bigger than that. Okay, so you have all these functions. How this is very important to computer scientists to understand where things are. Okay, so if you are here, if your algorithm here is fast. Okay, if your algorithm is here, it's slow. All right, so you obviously you want your algorithm to be on the left-hand side as much as possible. Okay. In fact, you might ask, what kind of algorithms take factorial time to run? Can you think of an algorithm that takes factorial n to run? N things. Let me give you a problem. Right? Suppose you have 3 cities. Okay, you like to visit these cities in some order. How many possible orders are there for you to visit the cities? Right? So we will write it down. So I can go to 1 first, then 2, 3. So I can go to 1, 3, 2. What are the other ones? 2, 1, 3, and 2, 3, 1. Right? And then 3, 1, 2, and 3, 2, 1. So given 3 cities, there are 6 possibilities. Okay, so it's not an accident actually. This 6 is 3 times 2 times 1. It turns out to be the factorial of 3. Okay, so in other words, this problem of visiting, if you're going to find out how to visit n cities, let's say you have 1,000 cities, then you really have to consider 1,000 factorial permutations. It's a lot of permutations. Your computer cannot do it. Okay, it's not possible. All right, so you can see the limits of computing. Even a simple problem like that. I only got 1,000 things. I want to know which order I can visit these 1,000 things. The problem is there's 1,000 factorial possible permutations of 1,000 cities. Okay? So it's a huge problem to solve. That's why the people are really, hopeful about quantum computers and other computers that can run really fast. Because with the current computers, you might not be able to do it. Obviously, you can probably use a supercomputer to solve this thing. Maybe but you still have to work a lot to get to meaningful level, right? It might take a while to do it. Yeah? Or it's sometimes it's impossible to do, right? Okay, so we ordered the things, and then I'm going to give some names to these things. Okay, so the 1, if you can get your program to run in constant amount of operations, this is called a constant. So in other words, we call them big O of 1. Okay, so this is pronounced as big O. Big O of 1. Okay, big O of 1 means constant number of operations. It doesn't mean one operation, it means that some number of, like swap. Right, if you want to swap, you have to do 3. So that would be big O of 1. Okay, swap is big O of 1. And this is called a logarithmic algorithms. These are also good. Okay? And obviously you can think of what algorithm can be square root. I don't know. But we probably will find some. And these are called linear. Okay, they are called big O of n, and this is called big O of log n. The base doesn't matter, okay, so the base can be anything because you can always easily do a base conversion to get that. And these algorithms are called linear arithmetic. Linear, okay, this means it's almost linear. If you actually graph n log n, it's almost linear because log n is so slow to grow. Okay, and so this is called n log n, big O of n log n algorithms. And this is called a quadratic algorithm, so this is quadratic. Okay, so this is called big O of n squared algorithm. I'll give you like a simple way to find this big O. It's not a big deal. It's not a big deal. It's a big O, right? Okay. And then when you get to this side, these are called exponential algorithms. These guys. Okay, so they can all be in a class like this. Big O of 2n means it's really bad. Yeah, that's what it means. If you have an exponential algorithm, forget about it. because it's not going to be a useful thing to do at all. Okay? Because when you go work for someone, it's not just important that you can write a program. The important is, first, main thing is that can you write a correct program? The second most important thing is, will that program run fast enough for you to be part of a business application there, right? So it's very important to think about the efficiency. I think hopefully when you go to the next course, maybe they'll ask you to do some efficiency tweaks. Right? Can you make your program faster? Right? But it matters when you have like 10,000, 20,000, 100 million, data. Okay, so this type of an algorithm, this is the algorithm that we wrote early in the course. It's called max of 3. If you look at this algorithm, you can count the number of operations as 1, 2, 3, right? And then maybe this one 4, 5, maybe 6, 7, right? So something like this, right? So you can write 1, 2, 3, 4, 5, 6, 7, 8, and maybe this is another operation that would be 10. So you have 10 operations, but if you have 10 operations, you don't write big O of 10. You write big O of 1. Okay, so when you write big O of 1, what that means is, so for example, if you have a program that has a constant number of things, it doesn't matter, it doesn't depend on n, then the big O of this algorithm, okay, so is actually big O of 1. Okay, big O of 1. So when I say big O of Tn, that means Tn is the algorithm. Okay, so think about Tn as the algorithm, it's big O of 1. So this has no loops, there's no n. So it's just a bunch of, constant number of things you will do. They're not that interesting in terms of analysis because, it will run fast. So it'll run in microseconds, this whole thing, right? It will take that long. But things like linear search, right? You're going one at a time. Or you're finding a max. You're looking for the maximum element in an array one at a time, right? This will take n time, whatever it is. Like it could be 3n, it could be 4n, but it will be proportional to the length of the array, whatever you're doing. Okay, so you can abstract away all the constants and other things and just worry about n. Like something like find max, the same thing. You go to the end, that's going to be linear, what we call a linear algorithm. And second largest is the same problem. Essentially, you find the max, you find the next one, right? One way to find second largest is so you can have an algorithm like this. You can say, let me find the max, remove it from the list, and then find the next max in the list, right? So you run max twice. So maybe it will take n times for the first max, n times for the second max, so it's 2n. But 2n is still linear. It's still called big O of n. So here's an example of a quadratic algorithm. This one, what this does is to actually print a double array. So this is not really hard to understand either. Why is it running n squared times? Because all you're doing is, say that you run, so it's printing this 3 by 3 grid or whatever. So let's say n by n grid has n squared things to inside, right? You have n rows and n columns, and you have n squared things to process. So you can see that this is actually processing n squared things. So sometimes it's easy to just multiply the number of times this runs, number of times this runs, and get the count for the entire thing as n squared. So if you have like 3 loops, it would be n cubed. You have to be careful a little bit. Sometimes it doesn't work exactly that way. All right, so what is the technique for finding big O? First, you count the operations. Okay? Then you write the sum as a function of n. And then you drop all the terms except the highest term of the highest power of n. So let me give you an example of that. Say, for instance, we look at the algorithm and you count operations. Okay, when you count operations, you came up with Tn equals maybe 2 times n squared plus 3 times n plus maybe 5 other constant operations that we do. okay, outside of the loop. So you can imagine that maybe there's a double loop here, there's a single loop here, right? So what it says is that write the sum as a function, write the sum as a function of n, drop all the terms except the highest terms. So I'm going to write an approximated by 2n squared, okay? And then it says drop the constant in front of the highest power. Okay, so then we call this actually big O n squared. So in other words, all we are saying is this, these constants don't matter in the long term, right? Because as n goes to infinity, things are going to be dominated by n, whatever the power of n. Let me show you one thing, because I think I asked the question, I never answered this question here, right? Right, but I can try to answer. I don't know whether it's the right way to answer, but it's a way to answer the question. So here I have a program. Okay? What it does is, if you give me an n, I will print out from 1 to n. Okay, I will print out the following. I'll print out the I, which is whatever thing I'm looking at. I will look at the log of I, log of that I, and then I'll look at the square root of I, then I'll look at the I itself, then I'll look at the I log I. Now again, this is math log from so I don't know what the base is. I think the base here is like log base E, if you're familiar with E. Right? And then I compute I squared, then I do the 2 to the power I. Okay, so note what happens when I run this. Let me see you there. So if I'm already compiled. So let's say I run it for 10. Okay, so this is what I get. So this is I. This is log I. The second column is log I. The third column is the square root of I. Okay, you can see that it's already square root is kind of bigger than a log, right? But let's do it for 100. So this is the first 100 numbers. You have the first column is I, second column is log I. So notice the log I is like 5, right? This is the square root of I, the third column. So square root is still dominating the I. And then you have the, this is I, then this is the I log I think. And then finally, this is a very large number, right? This is like 1.2 times 10 to the power 30. Okay, this is 2 to the power 100. So it's a large number. In fact, if I run it for like 1,000, still it's okay. It's 2 to the power 301, 10 to the power 301, I think. And notice how, still the log is 7, and the square root is like growing, right? If I do it for 10,000, okay, now can I do it? So 2 to the power 10,000 can now be computed. It calls it infinity, right? All right, but still the log is 9, right? Log is 9. So log is a friend, right? So we actually, did we really answer this question? The log n is less than or equal to square root of n? You think we answered the question? No, from a mathematician's point, you didn't. Right? You just ran an experiment and you proved to me up to about 1,000 it's true. But how do you know it may not be true for 100,000? You don't know that, right? Right? So how would you prove it? Yeah. That's it? Okay, so this is the time you find that calculus is going to be useful, okay? So take the log of n divided by square root of n. Okay, take the ratio of the two, and take the limit as n becomes very large. Okay? Now, what rule do we use to find this? L'Hopital's rule, right? So there's a L'Hopital's rule you use to find the answer. The answer is either going to be 0 or the answer is going to be infinity, one or the other. Which one do you think is the right one?
0.
The answer is 0. Okay? Answer is 0 because log n is smaller than square root of n. So this guy is dominating more and more and more, so it's getting closer and closer to 0. Okay, so mathematically you can answer that question without even running any experiments. Okay? So that's an interesting thing. In fact, but the computers are really useful for at least thinking about whether the answer is right or wrong. Right? When I was doing my PhD, one of the things I did sort of like mathematical computing, computational mathematics, which is sort of like computers kind of shows you what might be true about certain mathematical things. And then once the computer confirms it, you still have to prove it. Right? You have to prove mathematically that it's true, just like the L'Hopital's rule or something. And therefore, it doesn't matter whether you have a Mac machine or Windows machine. Your results is always true. Right? That's very important. Okay, so you can ask the question now. We know this log is really a nice guy, right? Log, it seems like it doesn't really increase that much, right? But let me give you a problem. In fact, we know that if you take all the atoms in the universe, the total atoms in the universe, and take the logarithm of that, it's still a reasonable number. Okay. So if you have a logarithmic algorithm, then you can process a data size of the size of the total atoms in the universe, which is huge, right? All right, let me give you an example and ask you what you think is the big O. So all these examples, I want you to find big O of n. Okay, so the first example is this. For int I equals 0, let's say I equals 1, I less than or equal to n, I plus plus, a sub I is equal to I. So we're going to do some exercises to find big O for a given piece of code. Right? What was our, here's our technique for finding. Right? Count all the operations. So what is it? I'm only care about this, right? So there's one assignment here. Right? How many times it's happening? N times, right? So this is Tn equals n. Then it says drop all terms except the highest term. Well, there's nothing to drop here, right? And then drop the coefficient of the highest term. There's nothing to do. So therefore, we say that this is big O of 1, or big O of n. Okay, that's the answer. Let's do another one. Suppose I change the problem to this. I equals 1, I less than or equal to n, I plus equals 2, ai equals I. So I change things a little bit, right? In other words, I'm not increasing I by 1. So what is Tn now? If you give roughly, that's okay. It doesn't have to be exact, right? What? N over 2. Okay, now Tn is n over 2. Because you're only doing half of n, right? Because you're going up by 2 every time. Okay, this is like 1/2 of n. Well, what is the big O of this? Still n. Okay, so in other words, this problem and this problem both belong to the linear algorithms. Okay, they're the same class of algorithms, which is a very important thing for computer science, right? So let me do another one. So this time I'm going to do something different to the loop. For int I equals 1, I less than or equal to n, I will do something like this. I equals I times 2. okay, is by is equal to I. So now I'm multiplying the index by 2 every iteration. What's happening now? So we are trying to sort of describe the number of operations. In other words, you're saying, how many times I come into this loop, right? That's the question you're asking. So you want to know about Tn. How many times I'm doing this assignment? Okay, now, here's a technique, right? I do it, you should do it. If I cannot figure this out just by staring at it, right? The best thing to do is run the thing for some n's. Let's say n equals 10. See what happens, okay? See how many times it runs. If n is 10, the I will go from what? I will start from 1, it'll become 2, it'll become 4, it'll become 8. It won't do anything after that, right? So it will only do this 4 times. What if you make n 100? How many times are you going to run this? So again, if you make it 100, you get 1, 2, 4, 8, 16, 32, 64. 64 is the last one, right? So that's like 6 times, right? If you make it 1,000, it goes like 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. 512 is the last one, right? What is 512? 512 is like 9, right? So now you see a relation between these two. Like in terms of n, what is the relation between Tn and n, right? If you plot this, the graph, you will see that, here's n, here's Tn. It's probably something like this, right? Okay, in fact, what do you think this function is? It's not exponential. If it's exponential, it should go really fast, right? This is very slow. That means n can get bigger, but the outcome is slow, right? So in fact, this function here turns out to be the log base 2 of n. Okay? Because if you think about roughly, I don't want to be precise here, because if n is 10, what is log base 2 of 10? That means what power of 2 is closest to the 10? It's the third power, right? Plus 1 will give you 4. If n equals 100, what power of 2 is closest to the 100? It's the sixth power, which is 64, right? That's what you get this. But you can say, I think this may be 7, I don't know, I'm not sure. But it's roughly that, plus 1, plus, minus 1, whatever, right? So here's an example of an algorithm that is very efficient. It runs in log n. But what is the pattern here, right? That's the important thing. Because if you run a loop, and if you double the size of the index, you're getting to the end really fast. Right? You're getting to the end really fast. Now, there's another algorithm that we're going to learn, which I may have mentioned before, if you're given an array, say this array is like sorted, right? So let's say that this is 5, this is 11, this one is 13, 17, 24, and 50. Let's take a sorted array, okay? Now, I'm looking for a target. Let's assume my target is 5, right? But I don't know where this target's going to be, right? I don't know it's at the beginning of the loop, the array, or the end of the array, right? Of course, I can look at the beginning and check something. But a technique I can use is that I find the middle element of the array. Okay, then I compare this 5 to 17. And because 5 is less than 17, I know if this element exists, it should be on the left-hand side. Right? And then I take this side, okay, and then look at the middle element of that. What algorithmic technique I'm applying now? You guys just went through it in the test. What is this called? I'm looking at a big one. It's called recursion, right? See, I'm doing recursion now. I'm taking the big one. I'm trying to solve a smaller problem, and a smaller problem, and a smaller problem. Hopefully I'll get to the answer, okay? So then I look at this array, middle one. Now 5 is less than 11, right? So therefore it's got to be here. So now I have an array of size 1. At this point, I look at the middle, which is 5, which is equal to this, I'm done. Right? How many comparisons did I do? I did 1 here, 2 here, the third one I'm done. Right? Third one I'm done. But notice the array size. Array size is 6. Right? Array size is 6. Think about what you get if you take the log base 2 of 6. Okay, log base 2, 6 is like, I guess 2 squared is 4, right? 2 to the 3 would be too much. So what I know is that log base 2 of 6 is something like 2 point something, right? Log base 2 of 2 point something. Now, if I take this log and round it, okay, so if I round this, I get 3. So that's exactly the number of comparisons I have to make in the worst case to find this. So it's going to be round of the, whatever the logarithm of the size of the array. So here's another problem that is logarithmic. Because here, I'm not increasing by 2, multiplying by 2, I'm dividing by 2, right? So you can come down dividing by 2, or you can go up incrementing by a factor of 2. Right? This algorithm is in fact called binary search. We will write the code next time, right? Binary search. But will it find it if the target doesn't exist? The same algorithm? Let's see. Suppose I give 6, right? So if I give 6, then I come here, compare it to 17, 6 is less, so therefore it should be here. Then I find the middle, 11, 6 is less, so it should be here. Now I compare 6 to 5, but my search space is now only one element, right? Because 6 is not 5, I'm done. So I'm not dividing anymore because I come to a point where I'm looking at an array of size 1. So once I get to that, either it's there or the target is not there. Okay, so that's the conclusion you make about the about this. Okay. So what do you think of this stuff? I don't know what you're thinking, right? What is it? It's very mathematical, right? What I'm doing is a lot of math, but math is very important to computer science. So if you hate math, consider changing your major because it's going to be really hard to survive in the computer science program. I'm not, you just have to like math. You don't have to love it. Okay? But, math is something that, I don't know how people learn math, but, math, like anything else, you have to do a lot of practice, right? I mean, I didn't become good at math overnight. I solved a lot of problems over time, and, that's how you become good at anything, right? You have to spend, what? If you want to be an expert, how much time you have to spend? 10,000 hours, right? You have to spend 10,000 hours, right? 10,000 hours, right? You have to spend 10,000 hours trying to be an expert in something, right? Anyway, so this stuff is really, I think it's going to be on the final exam. This means that you should be able to look at a piece of code, count it, and see what the big O thing for that code would be. Right? We will continue to look at, from now on when we write programs, we'll always think about big O. When I write an algorithm, before that I didn't ask you that question, right? But from now on, if I write some algorithm, then I will always ask about the complexity of that algorithm. Okay? So let me give you, I still have a few more minutes, so I don't want to, do we have classes next week?
You want to cancel one?
Oh, you want me to cancel the class?
Yeah.
I don't know.
I love computer science stuff. Right?
Look, I mean, I love this class. How can I cancel?
Well, we just took the midterm. Give us a little reward, I think I do pretty well.
We'll think about it, okay? What?
For Thanksgiving?
Christmas present? Is that what you want?
I want to learn for Christmas.
All this time I have the feeling you guys love to see me, but I get the feeling now you don't. Right?
Christmas present is a cherry on that.
Oh, first family, then you now, right? Okay. All right, I'm the second. Ah, that's okay. No, that's true. Okay, so let's do a few more problems here, right? Oh, not a few more, but let's just do this, okay? So, yeah, question? No? Okay, less than or equal to n. Okay. So let's take that example, right? So I have a loop, I from 1 to n, and another loop, j, from 1 to n again, but the j I double the j, right? But I will increment I by 1. So the question we're asking is, what is Tn? Right? How many times this is running? Now, one technique that you can use is that these two loops are kind of independent, right? In other words, this is an I loop, and there's no I here, right? So j is totally in charge here. So what we are doing is this. If I equals 1, the j, how many times the j runs? The j loop. Yes? So, this, now forget about, you already did this.
It's n?
No, it's not n. What? It's a j loop that gets, the j gets multiplied. What's that? No, this part, is this log n? Why is it 2n?
Because 2 times equals 2.
Yeah, that means j equals j times 2. Right? So j equals j times. So we already did this part, right? Independently we did this. So that means j runs log n times. And then if I equals 2, the same. Right? If I equals n, the same. And therefore this whole thing runs how many times? It runs n log n times. Okay, so here's an algorithm that's n log n. The only way I can say that is that because if two things are independent, it's okay to know how many times this runs and how many times this runs, and just multiply them. Okay, but you couldn't do that if you have a situation like this. Suppose you have something like this, for int I equals 1, I less than or equal to n, I plus plus, then you have for int j equals to I. J starts from I. Okay, and then j less than or equal to n, and j plus plus, and then you do something with aij. Right, this is kind of different. This is dependent, right? Because notice that the j kind of depends on I. So you couldn't multiply if you say, you know, you could actually do it like this. Okay, so they are. If you want to analyze it the same way, you can say something like this. If I equals 1, right, j, how many times the j runs? I mean, you already did the nested loops, right, yesterday. So if I equals 1, it's fixed. J starts from 1, goes all the way to n, right? So j runs from n times. Right, j runs 1 to n times. If I equals 2, how many times the j runs? So now you start from 2 all the way to n. Right? How many times is that? N minus 1. Okay, because 1 to n is n, but if you don't write the 1, then this is n minus 1. Next you go 3, you run your j from 3 to n, this means n minus 2. Okay? So finalize n. Right? Finalize n, that means if I is n, it only runs one time. Right? Because if I equals n, then it runs from n to n, only one times. So the total number of times this thing runs is going to be the sum from 1 to n. Okay? Do you know how to find the sum? Remember we talked about this, a technique for finding it? Yeah, so you can say to find this sum, all you have to do is add the first one and the last one and the first one. You get n plus 1, right? But then you add the 2 and the previous one, 2 and n minus 1, you all still get n plus 1. So you get n plus 1 n over 2 times, because you only do half of it. Okay, n plus 1 n over 2 times. So you can just say something like this. Then in that case, the Tn is going to be n over 2, n plus 1. Okay, n over 2, n plus 1. If you expand it, just algebra, n squared over 2 plus n over 2. Right? In Vigo analysis, you drop the low order terms, so it becomes n squared over 2, which is the same as 1/2 n squared. Now to find Vigo, all you do is just say drop the coefficient, and we say this algorithm is Vigo of n squared. Okay, so all I did was, I mean, this is a little bit harder algorithm for you to understand, but you will see this either next week or the week after. This is like a sorting algorithm. This is the kind of structure you set up for sorting. Okay, so you will see that this is not very uncommon. This kind of thing can be used for something like sorting. So the sorting can take n squared time, right? Okay, so I showed you some examples, and yeah, this is right. Okay, so what's your plan for Thanksgiving? Are you going home? Going home?
What's your plan?
my plan, I'm going to Pittsburgh. Yeah, that's where I lived a long time, long part of my life. I lived in Pittsburgh, and I had to go say hello to Steelers. Yeah, and yeah, I'll see you guys. I have to confirm with the coordinator to make sure it's okay. All right, to think about the next week classes, because if there's something to cover, I have to think about how to cover that, right? Because I can't skip a day. But we'll see how it goes. You guys are not going home this weekend, right? Yeah, you're going to wait. Okay, see you.